put the microphone this way. Okay. So let me just ask you, who's doing deep learning experiments for a living here? Maybe. Okay. Who's more like hobbyist or student? Okay. And who's not doing it? Is just interested. Okay. So all in the back. Interesting. So and who's using TensorFlow for those who is not using it? Okay. All right. So I think it's all a bit of a mixture. So I'll talk a bit about the basics of what CNTK does, which is very similar to some of these other toolkits. And then I'll talk a bit about the specifics of what makes CNTK different, and maybe should give you some good reasons for trying it as an alternative to TensorFlow or Caffe or any of the other toolkits. So first of all, what has Microsoft to do with deep learning? Well, in fact, Microsoft had its first AI program in 1991. So whatever product you see from Microsoft has probably some neural net model, or at least a different machine learning model built in, whether it's Cortana or Bing or Skype. And quite recently, like half a year ago, it has reorganized itself and formed a big group which is called AI and Research, which is about 5,000 people globally. So it has all of research in it, and also a lot of product teams that are working towards these products. And so the group that me and William and also some other people down back there at the table are coming from is actually part of AI and Research, and we're in Munich as well. So some contributions from Microsoft, for example, is image recognition, where ResNet is a development that many of you probably know, which was developed in Microsoft Research Asia in Beijing. And here is another result from the speech team, which was last year, where they, for the first time ever on a standard corpus, which people had been working on for 20 years or so, achieved human parity. And actually some people on this picture have been the first authors of CNTK. So this is Dong Yu and Frank Seide. So they're basically the nucleus where this all started. So it started as a speech tool, which was already open sourced 2 years ago, but nobody noticed. But because it wasn't on GitHub, it was on Codeplex, which meanwhile doesn't exist anymore. So this was tagged as a generic toolkit for deep learning, but it had still some constraints because people were coming from speech, and it wasn't really used outside of the speech community. So it was restricted in quite a few ways. But in the end, it's very similar to some of the other toolkits in that it allows you to define a model, train it, and obviously evaluate it as well. The focus was, because it was coming out of the speech group, that those people actually had a lot of RNNs that they wanted to train, and on a very large scale. So even 2 years ago, you could do distribution, you could run it on multiple GPUs, and it had a very efficient implementation of RNN. So that hasn't changed. It's still at the core of CNTK. What is now much easier with the 2.0 release, which was released just a week ago or so, is that in addition to having the fastest RNN implementation out there and having very simple to set up parallelism and data reading as well, because you often wait for disks or CPU to shuffle the data into GPU. There was a big push towards APIs and flexibility. And that was where it was lacking before. It was basically just a C++ program with some configuration file. And then a library was developed, which is also still pure C++, which was then exposed to some of the standard languages. So the first one being Python, but also there's some .NET and Java binding. There's also a built-in standard layers library. And for those of you who know TensorFlow, there's this plethora of libraries. So at least CNTK comes with a standard one that is optimized for this toolkit. And now, brand new, there's also a Keras backend, which I talk shortly about at the end. So a deep learning toolkit needs to answer these two questions. So how do you define them, and how do you execute them? And you want to split that apart in the sense that you want to be able to run the stuff as fast as possible. So you need to be able to go on CPU or on GPU or any other kind of hardware. So you need to have some kind of declarative mechanism on how you define a neural net. And well, if you usually come from literature, the way you define a neural net is just by a mathematical formula. So in this case, we have just a feed-forward network, which consists of some input x, which is just run through a linear projection here with this w and some bias term, and then you have a sigmoid after that, and you pass that on to a few layers, and through a softmax function, and that defines your neural net architecture. And then you might have a loss function, cross-entropy, it's another formula. And so what's the best way to write that down? And in CNTK, this is just basically the same thing. Right, so this is Python code. If you haven't seen the @ sign, that's a pretty new addition. So if you have an older version of Python, you can also use the old way. But this definitely, I mean, what you see already is that one of the design targets was that somebody who is familiar with the formulas should be able to write this up as easily as possible. And so then once you have this kind of description, by the way, who's using PyTorch or Chainer? Nobody, okay. If you have such a description, you have a specification of how the network should look like, and now you can take this and turn it into a graph that you can actually compute. And so this is what it's done. You have these primitive operators that constitute this graph, and all you need to do then is to say, okay, so what are my parameters? What are my inputs? Here's my network. And you're done. So now the only thing that you have to do is feed in data, which you can do either by feeding it arrays, or you can attach it to a special reader, which reads stuff from files and is optimized in a way that it does prefetch while you're computing and stuff like that. So there are some things that are built in. While you're experimenting, you might just read the data yourself and put it in a NumPy array, for example. And that's it. Then there are some things that allow you to define things on a bit of a higher level. So one thing that you notice is that this formula for a feed-forward network is often also called a dense layer. And so you can use this built-in library to go from these primitive mathematical operators to higher functions. So what other toolkits might call layers, you would usually call it a function in CNTK, because that's what it is. The whole neural network is just a big function. What you also see here is that the layer definition is separated out from the input. So you say dense, and then you give it a few parameters. And once you want to plug it into a graph, you also give it an input. But these two steps are separate. And that means that you can also do things that you might actually only know from like functional programming languages, where you have operators which basically model function composition. So this is the same graph, just written in a slightly nicer way, where you just say, all right, so I have some input and it flows through this network through a bunch of layers, and that's my model. And then in the end, you have to attach it to some input variable. And if you want to do this even in a way that it looks nicer, you can also write this as a function. So since you cannot train Python functions, this is a very simple way to just treat it as such. So this just means we have a function which computes a neural network, which expects a tensor, and there might be different types of tensors of size m, and another tensor of size j, and that defines your network, and then you can pass that function to the trainer. Right. So this way you can combine these different functions into higher order functions. I already mentioned this network of dense layers. You might have a recurrence block here, where you put you do an embedding lookup first, and then you pass that on to a recurrence block, which takes an RNN unit or an LSTM unit, and then you feed the output further to a dense layer. And this is how it looks like once it's expanded. So in the middle, you see the graph of operations that is generated from this first line. And it already has a bunch of things that you've seen on the first slide. So you see there's a parameter matrix W. There's a placeholder, which is an unbound variable that still needs to be bound at some point. It goes through a dense block and a sigmoid and so on. And so now you have another function which, here on the left, which defines the multiplication, and then once you put those together with the criterion function, you get just a bigger block. Now what is probably not very visible is that some of the parameters are still unbound here on the middle part. So some of the tensor dimensions are not given while you're constructing those blocks, but they might be inferable once you put the whole function together. And so here on the right side, all of these three parameters have been resolved, except for one, which is what is called the dynamic axis, and I'm coming to that shortly. So usually in every other toolkit, the tensor dimensions are fixed. CNTK has the ability to keep one dimension not fixed, and that's just because you want to deal with RNNs in a special way. Yep. So the list of layers is, as you see, for those who have been training neural networks, I think it's I don't know if it's complete, but it's at least it's a good starting point for doing most of the typical problems that you might face, from convolution to more sequential operations. Yeah, and if that's not enough, you can also, thanks to some person here in the back, also write your own operators in pure Python. And why is that special? Because CNTK is a C++ system. So if you want to write your own operator, actually C++ will call out to Python, which is not what you usually do. But it often enough, the extended operator that you need is actually in the loss function. And so it is often not that time critical. So writing stuff in Python is a bit slower. You need to copy things from GPU to CPU, for example. But at least it unblocks a lot of scenarios, and you don't have to touch C++ to implement them. And so all you need to do here in this left example, this just has its own implementation of the sigmoid function. And you can just write this in pure Python, or usually you would use NumPy for that. And so the tensor that comes in the forward pass is available as a NumPy array, and then you can work on it and return the results. And you have to supply the gradient as well for the backward pass. And that's it. And you can do the same if you want to apply, add your custom learner. Knock yourselves out. Right, so, but how does it look like when you're working with recurrent networks? So now you have to model that time dimension. And the way you do it, if you look at a paper, and if you're familiar with the math, you would just define it based on the current time step and depend on the previous time step, for example. So you would write a formula like this, where you have some index t and then an index t minus 1. And so then this fully defines this construct. Now, if you want to model this with your normal deep learning toolkit, you basically have to unroll that loop yourselves. And in CNTK you don't, because it's all inferred. You only describe how you want the output to be, and it does everything automatically. So there's just one special operator, which is called passed value, and that just takes the element that is given as an argument at the previous time step. So how does that work internally? We have this same function, and so what we do when we have this passed value, it actually detects that there is a cycle. So it goes over that graph and does cycle detection, and it would group these red operators which form that cycle into a special sequence operator that like on the lowest level performs that looping over time. And yeah, here's how you would write it in TensorFlow. So you would do that looping up front, and you would basically expand that loop. Yeah, and this is actually what gives CNTK a big advantage, because if you have this declarative version of a loop, you can come up with optimized implementations for it. And so there is a performance benchmark which is done by a university in Hong Kong, which has been doing this for a while. And you can see that if you're running convolutional neural networks, CNTK is sort of on par or a bit faster than some of the toolkits out there. But in fact, convolutions are just exposed by NVIDIA. So all what these libraries usually do, most of the time they're just calling out to cuDNN, and what you're seeing here in the benchmark is basically just the overhead of the toolkit for calling this. So there's not much to gain there. But the situation is very different for RNNs, and you can see that here CNTK is a lot faster. The numbers are showing the V8 version of that benchmark. So the people at that university have iterated on this quite a few times over the past year. Unfortunately, the TensorFlow numbers are missing from that last one, so it's showing here the V7 numbers. And that is roughly what you should expect. It's also what is reflected in our experience, because we also have people who work with TensorFlow and Caffe and other toolkits. And so we know that often enough, people complain about training times with TensorFlow, and then once you do a CNTK implementation, sometimes you get a 10 times speed up if it's a recurrent model. But at least you get a 2 times speed up. So that's roughly what one could expect. And if you think about training times of 4 weeks versus 1 week, that might actually be the difference between doable and not doable. So how is this used? How can we take advantage of this automatic loop unrolling? And so what we can do is we can organize sequences more efficiently internally. So if you think of a mini batch, which comes in different lengths. So that's the first thing to keep in mind. They don't have to be sorted by length or anything. So the first sequence, or time time-oriented tensor, or tensor with a time axis, comes in and it's put in memory. It's somewhere, at the start, I guess. And now you read in more sequences from the same mini-batch, and they might have different lengths. So now you have a lot of slack here on the right that you want to take advantage of. And CNTK actually does this. It internally packs the sequences efficiently in memory. So now as more sequences come in, you're almost optimal, right? So this is a typical case. There are some entries where you still need to have padding, but to the extent that you can actually distribute these sequences in your rectangular structure, CNTK allows you to do it. And so now for computing the forward pass, every time step is dependent on the previous one. So there's no way to parallelize it. But what you can do is to compute one column at a time. Right? So because these sequences are independent of each other. And so that's what it's done. And the only thing to do then is to make sure that as you reach this boundary, that you reset the state of just this sequence to compute the next one. And then for the padding, it's just garbage in, garbage out, so you don't really care. So that's the difference. So if you look at other toolkits, you have to have this the same time dimension. So you have to, first of all, think about what is the maximum time dimension that I want to support. And then you have to either accept that it's very inefficient because you might have different lengths in time, or you need to sort your training data. So that's what's often done, that you pass in all sequences of length 20, and then you have this just filled up. So this is not necessary. You don't care. The readers that read in the data can actually do perfect randomization, and that actually helps the model training as well. So it has a lot of advantages. So you fully randomize the input, and by being aware of the sequence lengths, you can actually do better backpropagation as well. In short, you don't distribute mass of the gradient onto the padding, if you will. So you don't prefer, or you don't give advantage to short or long sequences. Every sequence is treated the same. And that together has given the speech team 1 to 2% better accuracy in the end. So it was very big for them. The other component that you need is efficient parallel training at some point, once you go beyond Kaggle data sets, or so, once you go to real-world data sets. And the most important type of parallelism here is data parallelism. Usually the models that you want to ship fit on one GPU, but the data doesn't fit on one machine. And you want to take advantage of that as much as possible. Who has used distributed TensorFlow? Nobody. Okay. So the challenge, once you set this up, is the communication costs. And there's some numbers here. So basically what you see is that the communication cost for exchanging the gradients, if you do it in a naive way, is in the same ballpark as the compute per mini-batch on a machine. So the communication costs immediately start to dominate. So you need to do something about that. And, two things you can do. The first thing is to communicate less each time. And so there's a technique that is implemented, and it's also patented, so it's only in CNTK, which is called 1-bit SGD. And here you reduce the gradient to 1 bit, and you just keep track of the residual of the error that you still have, and then merge that residual into the next exchange step. And the other technique is called block momentum, where you communicate less often. So you aggregate the gradients over time, and then you have only certain sync points where you exchange the gradients between the nodes. All of them are also on GitHub. It's just a slightly different license, so you wouldn't be able to take that and put it in a different toolkit. And if you do that, then the scale up across GPUs is actually almost linear. So you can see as we go from 1 to 64 GPUs, this is on a speech task, you get almost linear scaling. And the best of it is that it's actually super simple to use. So there's actually only 2 lines of code that you need to change. The first one is that you need to start the Python process with the MPI executive. MPI, if you don't know, is a framework for doing process calls. So all you need to do is give it the servers that you want to communicate with, and that's it. And the MPI library just takes care of the rest. And then you need to exchange the learning algorithm with one that is aware of the distribution. And that's it. Right, so, and in the end, what you get is a file that you can use from the C++ API or the Python API or the Java or .NET API. So to summarize, the core strength of CNTK is performance and scalability. It was set up to be a production-ready system. It has the fastest RNN implementation that is out there. It has a very simple implementation of parallelism through MPI. And it also has fast data readers. I touched upon this only very briefly. 2.0 has these major updates on the API level, so you have a full-fledged Python API with a built-in layers library and this ability to add your own operators in Python if you want to try out new things. It runs on Linux and Windows. We actually use it both on Linux and Windows ourselves. And the internal version is the same as the one on GitHub. So there's no extra code hidden in Microsoft somewhere that we don't put out on GitHub. Yeah, and this is more or less a bit of an outlook because we now have a FirstCare backend. This was almost a vision, I would say, when I went to the CNTK team about a year ago and said, Keras is really important to get people use this stuff. And it also shows are there any functionality gaps. It also means that one can reuse the battery of tests that have already been written for Keras and so on. So we finally have this. And François Chollet thanks the contributors here. Finally, that is merged. It is right now a beta version. There are some release notes on this link. And so if you have been using Keras, it should be possible, maybe with some more documentation that is hopefully coming in the next days and weeks, to just try it out. The only thing is that Keras, the history of Keras is that it was originally based on Theano, and then TensorFlow was also more or less based on the concepts of Theano. So they're very similar. Whereas CNTK has, for example, this separate concept of what a dynamic axis is and how loops are done and so on. So right now, I think I wouldn't be able to say is writing it against the Keras API is just as efficient as using the CNTK API directly. But the expectation should be that for convolutional nets or feed-forward nets, it should be roughly on parity with the other network, with the other toolkits. There's a typo here, and it should be faster on RNNs. And there's still some examples which are not yet working because there's a few API calls missing. But overall, I think it's in a pretty good state already. Yeah, so if you want to know more, there's a website, shortcut cntk.ai, and it's on GitHub under Microsoft/CNTK. Please also put a star on it if you are interested. There's an alias if you are desperate, CNTK help. You can also go to Stack Overflow, and there's questions tagged with the CNTK tag. And that's it. And this is our lab. We're in Lehel. We also have a website which doesn't even have the address on it. So I'm putting it here. And if you want to look on Twitter and so on, here's the information. And with that, I would hand over to William. Are there questions? Yes.
Are there areas where you know you are using like, so I understand that you're faster than TensorFlow on a lot of examples. Are there areas where it's still good to use TensorFlow? And actually, when should I switch to a CNTK?
So TensorFlow, meanwhile, is a toolkit that has grown beyond neural networks. So you have some operators in there that are not implemented in CNTK, but they're kind of special. So for example, fast Fourier transform would probably not be in CNTK at this point. Otherwise, TensorFlow overall has a bigger community. So I guess you will find more pre-trained models. You will find more people who can answer your questions. And there might also be more support on like obscure architectures. So there are certainly reasons to use TensorFlow as well. If you want to do simple parallelism and RNN work, I would definitely recommend CNTK over TensorFlow, just out of our own experience. Yep.
And you also go back in time 2 or more times.
Yep. You can also go forward. Yep. Please. No, it's not very well known, so I couldn't. I guess it runs well on Intel CPUs, but usually everything is NVIDIA. So I would say, right now, if you look at the landscape, I would say for like general purpose, TensorFlow is certainly the most established. Maybe unless you want to really scale it up. Then for the vision community is usually Caffe. It's also fast on the deployment side. For an RNNs, I'm making the point that it should be CNTK. And then there's what is very popular now in the research community is PyTorch or Chainer, because they have even more emphasis on the flexibility side. So if you want to break the rules of what a declarative toolkit can do, they allow you to do it because you can there basically change your network at runtime. But that binds you to a language like Python. So that's not ideal for developing a model for production use. Although it's probably possible in many cases, but we are working in an environment where you often count the milliseconds, and so then having something that is really bare bone is key. I know that there are developments in CNTK to bring dynamic networks also to CNTK, but it's a bit early for that. So expect more to come on this pretty soon. More questions? Yep. Yeah, I mean, it's not bound. It's basically just bounded by memory. So there's no other limit, which is the same limit as everybody else has. We have managed to run out of GPU space, if you if you mean that. But hundreds or thousands of nodes are no problem. Yep.
What training infrastructure shall I use if I want to switch to CNTK? Because currently we thought about using Amazon Web Services as a means to scale up. So will I have to switch to Asia?
No, no. So the question was, what is the hardware or system that you could use? So it is supported on Windows and Linux. We are using usually Ubuntu, but it's basically just a pip install and you get everything. You can use whatever VM. In the best case, it has a GPU. So you're not tied to anything. If you use Azure, you get CNTK pre-installed. But other than that, it's not tied to some specific system.
I'd expect Linux to be faster when I don't use the graphic, the GPU. So is Microsoft competitive with the GPU?
Yeah, there's not much. So the question is whether there's a performance difference on Windows or Linux, and there's no difference. I mean, for the operations themselves, they're mostly executed on the GPU through NVIDIA libraries, so they're the same. For CPU, we're using Intel MKL most of the time, and so that leaves the custom operations, and there you have small differences whether GCC or Microsoft Visual C is optimizing better, but I guess they're roughly the same, so it should be the same performance.
Are there any plans to bring CNTK directly into Microsoft Machine Learning Studio?
I'm not that familiar with machine learning, but I guess yes. I just don't know their product roadmap.
Oh, okay.
It's a different group. Microsoft is very big.
Any other questions? Yeah. Okay, so I think we're gonna have. Thank you again for a nice talk and nice answers. I think we're gonna have like 5 minutes break, and after we will continue with second tutorial. Thank you.